Now we begin the second category of forecasting models, which consists of machine learning-based parametric methods. The first model in this group is a multi-layer perception, or MLP. The MLP takes a set of input features and passes them through multiple nonlinear full-connected layers to produce a future power profile. It's the most basic and widely used neural network model. Let's start from the simplest case, a single-layer perception. Here, each input feature is connected to each output feature through a set of weights. The weighted sum is computed, a bias is added, and then a nonlinear activation function is applied. This produces one element of the output vector. Mathematically, we can express the single-layer MLP as follows. The activation function can be ReLU, tank, sigmoid, or any other nonlinear function. It introduces nonlinearity into the model and enables the network to learn complex mapping relationships. Now, let's look at the multi-layer version of the MLP. As shown in the diagram, instead of stopping after the first nonlinear transformation, we stack several hidden layers. Each layer transforms the representation into a higher-level feature space before producing the final output. We can write the general multi-layer MLP as follows. Here, each layer has its own weight matrix and bias vector. Stacking those layers enables the model to approximate highly nonlinear functions. Next, let's look at how the MLP can be used for forecasting tasks. In practice, there are two common ways to use an MLP for power prediction. The first approach is sequence-to-sequence forecasting. In this setup, for the daily forecasting task, we feed the past 24-hour profile and other features into the MLP, and the network directly outputs the next 24-hour profile. This approach tends to learn the overall daily shape effectively. However, since the output dimension is large, the model has a high risk of overfitting, especially when training data is limited. The second approach is sequence-to-point forecasting. Instead of predicting an entire 24-hour vector, the MLP predicts just the next time step. In this example, we use the lag length of 4, meaning the past 4 hours are used to predict the next hour. The newly predicted value is then fed back into the model as input to iteratively generate future forecasts until the end of the prediction horizon. Because it predicts only one step ahead, this formulation has a higher data utilization rate. It learns short-term dynamics more effectively and is easier to embed into model predictive control frameworks. Here, we conducted numeric tests with a hidden layer configuration of 64, 32, 24. Here is the sequence-to-sequence performance. For a high similarity case, the forecasting result is pretty well. For the low similarity case, the model still captures the general shape, but the deviations increases. For the sequence-to-point case, similarly, the performance is good when the source and the target datasets are highly similar, while it degrades in low similarity case and can even be slightly worse than the sequence-to-sequence model. Nevertheless, this approach is well suited for scenarios with limited training data and for MPC applications.